Hi, this is Alex from devstories.eu, Python Cheminformatics and AI, episode 5 of 22. AI models do not actually understand atoms and bonds. They only understand numbers. If you want an algorithm to compare two structures, you need a way to translate chemistry into math. Fingerprinting and molecular similarity is exactly how we bridge that gap. A molecule in RDKit is essentially a mathematical graph. The atoms act as nodes and the bonds act as edges. To perform fast computations on these graphs, we convert them into bit vectors, which are just long arrays of ones and zeros. This array is called a fingerprint. The logic is straightforward. If a specific structural feature exists in the molecule, a specific bit in the array is flipped to 1. If that feature is missing, the bit stays 0. By converting complex molecular graphs into standard bit vectors, we can easily compare them mathematically. RDKit provides several fingerprinting algorithms. The default RDKit fingerprint uses a topological approach. It analyzes linear paths through the molecule. The system starts at an atom and traces along the connected bonds up to a specific length, typically between 1 and 7 bonds. Every unique path it finds is passed through a hashing function, which assigns that path to a specific position in the bit vector. While topological paths are useful, modern cheminformatics heavily relies on Morgan fingerprints, often called circular fingerprints. Instead of tracing linear paths, Morgan algorithms analyze the neighborhood radiating outward from every single atom. When generating a Morgan fingerprint, you must define a radius. A radius of 0 means the algorithm only records the individual atoms. A radius of 1 captures each atom plus its immediate connected neighbors. A radius of 2 expands that circle one bond further. The algorithm catalogs all of these overlapping circular environments, hashes them, and flips the corresponding bits to 1. Usually we fold these hashes into a fixed length vector, like 2048 bits, to keep memory usage predictable. Morgan fingerprints with a radius of 2 are the industry standard because they capture functional groups and local chemical context beautifully. Let us look at a concrete scenario. You have two slightly different molecules. Maybe they share a large core structure, but one has an extra methyl group attached. You want to quantify how much they overlap. First, you read both molecules into RDKit. Next, you generate a Morgan fingerprint for each, setting the radius to 2. You now have two distinct bit vectors. To calculate how alike they are, you compute their Tanimoto similarity. Here is the key insight. Tanimoto similarity ignores the zeros. It only cares about the features that are actually present. The math is simple: intersection over union. RDKit counts the number of bits set to 1 in both fingerprints and divides that by the total number of bits set to 1 in either fingerprint. If the two vectors match perfectly, the Tanimoto score is 1.0. If they share no features at all, the score is 0.0. For our two molecules differing by a single methyl group, the circular environments around the core will mostly match, while the environments near the mutation will differ. You might get a Tanimoto score of 0.85, giving you a precise numerical value for their structural overlap. Keep in mind that mapping a complex molecule down to a fixed array of bits means losing some data, and a high Tanimoto score guarantees structural overlap, not biological equivalence. Thanks for spending a few minutes with me. Until next time, take it easy.